Another episode of Reasonable Coding. This is episode number 20, and tonight we're gonna be talking about the OCaml and Recent Native Garbage Collection, Garbage Collector, right? Or the runtime support for collecting garbage. Yeah, something like that. Okay, so I am recording. I have sent some links around. There you get a little bit of induction. Okay, so I'll just do one last check very quick to make sure that this is taking us to the right place, and in about a minute or two I'll just start digging into it. Yeah, it seems to work all right. Let's double check the volume, and by now you think I had this streamlined. Volume is good. Okie doke. So go back to the event. I'm gonna read the description so it's that obvious what we're gonna be working on tonight. So the OCaml Garbage Collector is a fantastic piece of software that allows us to write programs that are incredibly fast yet do no memory management on their own. By that, I guess I meant that we don't need to do the memory management manually, right? It's done automatically for us. It is also the same garbage collector that Recent Native uses, and that might come as a surprise to you, but Recent Native is essentially just OCaml, so many things are in effect the same. In this episode, we will dig into how it works theoretically. We'll play around with some of its APIs, and we'll try to map some of our program execution to it to better understand why it works and how does it work. So full disclosure, I actually know very little about how the garbage collection inside of Recent Native or OCaml works. So this is a learning experience for me as well. So tonight will mostly be about me learning how these things work. And hopefully we can all learn from the learning, if that makes any sense. Every now and then I'll do a pause for drinking water, like right now. And I had two references outlined for this. I also set 4 hours aside. It might not take 4 hours. It might be that after an hour we say, oh, okay, I feel that I am comfortable with the knowledge I've acquired, or I don't know, maybe I'm just tired after an hour of this and we need to cut it out. But until then, let's begin. And we'll begin by running through the tutorial in OCaml.org for garbage collection. So this is not a big piece of text, but it's a little bit. It might be a little daunting for some to start reading it, essentially because the two titles already begin with the words that you don't know about, and then proceed to name drop some concepts or some practices that you may not be familiar with, like reference counting, which is essentially keeping a count of how many points you're referencing a particular piece of memory, or explicit allocation. So I will begin. As with all modern languages, OCaml provides a garbage collector so that you don't need to explicitly allocate in free memory as in C and C++. As JWZ, and I do not know who this person is. James Werner Zawinski. Okay, American computer programmer with contributions to the free software projects Mozilla and Emacs. And he owns a nightclub in San Francisco. Alright. Piece of trivia done. He has a rant apparently for why Java sucks. And it says, firstly, good stuff. Java doesn't have free. I have to admit right off that after that, all else is gravy. That one point makes me able to forgive just about anything else, no matter how a Greg use. And since English is not my first language, I may need to search for some of these words. Outstandingly bad or shocking. Okay. Huh, interesting how the archaic sense was remarkably good. It was so good that at one point people thought, yeah, this is just bad. Okay. Given this one point, everything else in this document fades nearly to insignificance. But, ... Alright. So the OCaml Garbage Collector, and every time I say OCaml, I might as well be saying Reason Native. And I make the distinction between Reason and Reason Native because we're normally thinking of Reason as a language that compiles to JavaScript due to BuggleScript, right? That's the only reason. No pun intended. It's a modern hybrid generational and / incremental collector which outperforms hand allocation in most cases. Unlike the Java GC, which gives GC a bad name, I wonder if we should really have something like this here. The OCaml GC doesn't allocate huge amounts of memory at startup, nor does it appear to have arbitrary fixed limits that need to be overridden by hand. Interesting. Why would garbage collection be faster than explicit memory allocations as in C? It's often assumed that calling free costs nothing. In fact, free is an expensive operation which involves navigating over the complex data structures used by the memory allocator. If your program calls free intermittently, then all of that code and data needs to be loaded into cache. Displacing your program code and data each time you free a single memory allocation. Okay. I think this is assuming that I understand the underlying memory model of C. A collection strategy would freeze multiple memory areas in one go, such as either a pool allocator or a GC, pays a penalty only once for multiple allocations. Thus, the cost per allocation is much reduced. Okay. So GCs also move memory areas around and compact the heap. This makes allocation easier, hence faster, and a smart GC can be written to interact well with the L1 and L2 caches. Of course, none of this precludes writing a very fast hand allocator, but it's considerably harder work than most programmers realize. I'm starting to feel that this could use a few references. For example, it's considerably harder work than most programmers realize. What's a good reference to let most programmers do realize this before they get into writing this hand allocator themselves? OCaml's garbage collector has two heaps, the minor heap and the major heap. This recognizes a general principle. Most objects are small and allocated frequently and then immediately freed. These objects go into the minor heap first, which is garbage collected frequently. Only some objects are long-lasting. These objects get promoted from the minor heap to the major heap after some time, and the major heap is only collected infrequently. Okay, that makes sense. So I guess when they say generational collector, they mean that the minor heap and the major heap have two phases, or let's say two different frequencies for being freed, right? For being cleared up or garbage collected, and hence some of the things that are younger will always be in the minor heap, and as they get older, they will go to the major heap. And I wonder if the moving from the minor to the major heap is done essentially by the amount of references that as in referencing counting, right? That each memory block has. You will excuse my nomenclature or the words I use for naming things right now. It's definitely fluffy. It's something that I'm gonna be tightening up as I read the article and realize, oh, I shouldn't be using the word memory block for this. I should be using some other word instead. Okay, so the OCaml garbage collector is synchronous. It doesn't run a separate thread, and it can only get called during an allocation request. So this means only when we allocate memory is where we can clean up all the memory. Lastly, if you do know better than I do about these things, feel free to just comment out on the chat and call me out on any of my bullshit. I think it will be best for everybody. I will be thankful at least. Because then I will know, oh, this is not the thing I thought it was, this is something else. Perl has a form of garbage collection, but it uses a simple scheme called reference counting. Simply put, each Perl object keeps a count of the number of other objects referencing itself. Okay, when the count falls to 0, nothing is pointing at this object, and so the object can be freed. Which is interesting. Reference counting is not considered a serious garbage collection by computer scientists, yet it has one big practical advantage over full garbage collectors. With reference counting, you can avoid many explicit calls to close or close dir in code. For example, for each files my or die read from IO. This parallel code iterates over a list of files, opening and reading each one of them. There's no need to close the IO file handle at the end of the loop because Perl uses referencing. Okay, so as soon as it reaches the end loop, the IO variable goes out of scope, so the reference count on the file object goes to 0 and it is immediately freed. This is also not very clear. I expected close and close dir to be somewhat general concepts, not just Perl commands or Perl functions that you would be calling on the files. Consider the equivalent OCaml code. Let read file name, open a child in read from file. Okay. Calls to read file, open the file, but don't close it because OCaml uses a full garbage collector channel. This one over here, isn't collected until sometime later when the minor heap becomes full. In addition, OCaml will not close the channel when it collects the handle's memory. So this program will eventually run out of file descriptors. Okay, it's leaking. You need to be aware of this when writing OCaml code, which uses files or directories or any other heavyweight object with complex finalization. Cool. Sorry. To be fair to full garbage collection, I should mention the disadvantages of reference counting schemes. So each object needs to store a reference count. In other words, there's a word overhead for every object. Programs use more memory and are consequently slower because they are more likely to fill up the cache or spill into swap. Reference counting is expensive. Every time you manipulate pointers to an object, you need to update and check the reference count. Pointer manipulation is frequent, so this slows your program and bloats the code size of compiled code. They cannot collect so-called circular or self-referential structures. I programmed in many languages in many years, and I can't recall having created what? I programmed in many languages in many years and can't recall ever having created one of these. While I understand they may not be able to collect self-referential structures, I don't understand why this comment is here. Graph algorithms, of course, violate the previous assumptions. Don't try to implement the TSP in Perl. And that's the abbreviation for teaspoon, apparently. But I wonder if we can go quick search, graph algorithms, TSP. Traveling salesman problem. Gotcha. Right, there we go. Okay. So there's a module that's called GC that contains useful functions for querying and calling the garbage collector from OCaml programs. Here is a program which runs and then prints out GC statistics just before quitting. Interesting. So it's got an iterate function that will just iterate but multiply a bunch of floats by recursing over and decrement. So it essentially iterates from x init from R to 0. No, from R to 1, and then returns x init when you get 1, and then it multiplies all the floats. So initialize random, opens a graph, and then it will plot a bunch of dots there that are apparently random as well. So it will fill the matrix, the screen. And then after that you can call print stat with stdout, and this will print the stats into stdout. I'm assuming this is just a channel. We can just open RTOP and have a quick look. Oops, sorry. Yep. Out channel, oops. There we go. Minor words, total number of words allocated, promoted words, from minor to major, major words, heap words, free words, largest free fragments, compactions. We can see that minor heap collections are approximately 100 times more frequent than major heap collections. In this example, not necessarily in general. Interesting. Over the lifetime of the program, an astonishing 440 megabytes of memory was allocated, which is kind of big. Although, of course, most of that would have been immediately freed in a minor collection. Only about 128K was promoted long-term storage on the major heap, and about another 128 consisted of large objects which would have been allocated directly onto the major heap. We can instruct the GC to print out debugging messages when one of several events happen. That is, for example, on every major collection. We can... So we're giving it one value here. Try adding the following code to the example above near the beginning. So set something in the GC, and I actually have never seen this expression with field value. I assume, okay, it's just gonna, is the GC an actual object? What is this supposed to be? Updating a single field in the object resulting from the expression on the left. Should be mostly obvious what it does. So this is how we set the verbosity. We set the collector to be whatever we get when we call get from the collector, but we will replace one of the objects with this bit mask. Okay. That sounds right. Finalization and the weak module. I think we could just play around a little bit with this example first to try to get a grasp of what's going on and try to understand how this works before moving on to the finalization and the weak module chapter. We might not learn much though. It might be that there is not much that we understand yet, and this it doesn't make sense. But let's just do. recent GC. And we want to do reformat from this. Parse ML. Print recent in place do a.re. Boom. Same code, but in recent. I wonder why we have a spacing there. Okay, so now I guess we can just do tune. Oops. Tune file, executable, and then name will be A. And I think this should be all. Tune build. Unbound module graphics. Might be that we need to add modules graphics libraries actually. Where does graphics come from? Let's see. It might be that I haven't installed it. Might be. So let's do OCaml find, query, graphics. Okay. So it cannot find file graphics.cma. What does this mean? I don't think updating OPAM is going to solve this. This is also fairly old. Oh, I have to install OCaml enabling graphics. Right, so that might be a little bit of a blocker for this part. I wonder, perhaps we can do the operations without actually rendering anything. So I will go no further than an update. So I'll close this thing here. We will do the operations, but we will need to float. Where's iterate being called? Iterate. Okay. So that build default. If I call this, just running a few numbers, and then I get that on the end. Okay. So I guess that if I just ignore y, then I'll be able to just see the output, right? Minor, major compactions. This is a little more nicely split than it was before. I'm gonna move some windows around. I'm gonna move this thing to the left. Cool. And then we said we're gonna run this little bits over here, right? To change the behavior so that every time that there is what is it, an allocation of every major collection, right? Then we actually print the message. So I don't know what the recent syntax for this is, so I'm just quickly gonna go to recent try. I'm gonna drop this on the bottom box, and I'm gonna hop it to okay. So this is the syntax for actually updating a record. Yeah. Cool. So saving it, build again, it builds. If I run this, then okay. So this did 3 major CG cycles. And this seems to, oh, right. I can update later. Cool. So he's saying here that the docs say there's an astonishing 440 megabytes worth of memory, which I reckon will be the minor words. Now, if you're like me, you probably read somewhere before how much a word is in terms of memory, but you don't necessarily remember. So we're gonna search for that. So word size. Meant 16 bits. I guess we could go to Wikipedia. Right, so this is variable. Then, depending on the processor, it might be bigger or smaller. So, what does the OCaml? What does the GC output mean when it says minor words? And of course, if you know the answer to the question, please help out by writing it down on the chat. Hey, Minatia, I could not see your message before. I see it now on my phone. Thanks. Yeah. We get it. We get that the minor words are words in the minor heap. I was just wondering exactly what a word size is in this case. I guess what I could do is, because you see here it says that of the lifetime of the program, and astonishing 440 megabytes of memory was allocated. Naturally, I see there's a fairly big number over here. This is the total number of words allocated, right? But I don't see anywhere referencing what exactly is the size of one word here. So I'm wondering, is this the size of a word in a particular compiler, processor architecture? Or is this a different word size that the OCaml runtime defines? and then translates to whatever many words are necessary in the underlying computer. So a word will depend on the processor architecture, right? You may have words that are 1, 2, 4, 8, and so on bits. Anyways, I'm gonna move on, assuming that this is just a word of the underlying processor. So that's the first, well, not the first, but one of the assumptions I'll make is that here when they say minor words, this is actually this many, in my case, 64-bit words, right? Yeah, I agree. It's really good that we have a starting point, right, for the documentation. It needs some polishing. It needs some assumptions. It just needs clearing up what it's expecting me to already know. Like even a small disclaimer at the beginning saying, hey, this article assumes familiarity with the C memory management model, for example, so that when I read this, essentially, this, where is it? This little bit about what happens when you call free intermittently, then I go, oh, all right, I can relate it to my existing knowledge or to my already acquired knowledge. Right now, I'm drawing blanks because I do not know a lot about how the underlying model for C is. Anyways, I'll move on. Okay, so from here we have finalization and the weak module. We can write a function called Finalizer, which is called when an object is about to be freed by the GC. Okay. Yeah, that might be the math that we need to do. Right. So for everyone else that can't really read the comments on the live stream, me not, yeah, has said that if we take a look at this minor words, right, and we say the size should be around 440 megabytes, we can do for 40 megabytes by 124, that will give us the amount of kilobytes, and then if you do the same thing again, right, then you get this many bytes, right? And if we divide this by this number here, 1159 and 26165, then we get that each one of these words is approximately 4 bytes. So it's reasonable to think that each word in the minor heap will be 4 bytes. Which, of course, if we did the opposite math, if we just multiply this by 4, we would get a number that divided by 124 and by 124 again will give us roughly 440 megabytes. I think my heap size might be off. 1159.261.55. Okay. So yeah, we can assume that a word is 4 bytes for now. And yikes, yes, this is indeed, this feels like a lot, but I guess we could try to understand why we are allocating this much by analyzing this piece of source before continuing to the rest. So we will need to understand first how much will it take for each one of these variables to be defined, to be created in the heap. Since they're all floats, or most of them are floats anyways, yeah, float, either way it will be a float, and this is float as well. Then we would have to look at the memory representation of a float. And if we do that, I'm just going to open this again on the side. I'm going to close the Word. And somewhere in the documentation, in real world OCaml, there's a, we can go through that version. There is a chapter in the table of contents that talks about the runtime system, memory representation of values, blocks and values, integers, floating point numbers, and arrays. It's a box value in a separate memory block. It can be inefficient to handle large arrays of floats in comparison to box integers. Okay, so I guess this is an optimization for specifically arrays of floating point numbers. So we can perhaps go back a little. Okay. Many basic types are efficiently stored as unboxed integers at runtime. The native int type is the most obvious, although it drops a single bit of precision due to the tag bit. Other atomic types such as unit on the empty list. Where is it that we will find information about floats here? Floats. Okay. All floats. Oh, sorry, floating point number, there you go. As a block with a single field containing the double precision float. A block with a single field. So blocks and values. And a OCaml block is the basic unit of allocation on the heap. A block consists of a one-word header, and that's either 32 or 64 bits depending on the CPU architecture, followed by variable length data that is either opaque bytes or an array of fields. The header has a multipurpose tag byte that defines whether to interpret the subsequent data as opaque bytes or OCaml fields. I guess that's the tag byte? Yeah, there, here. Okay. The GC never inspects opaque types. If the tag indicates an array of OCaml fields are present, their contents are all treated as more valid OCaml modules. The GC always inspects fields and follows them as part of the collection process described earlier. So each one of the variables that we are creating, right, will be put in blocks that have this shape. The size field records the length of the block in memory words. This is 22 bits and 32-bit platforms, which is the reason OCaml strings are limited to 16 megabytes on that architecture. If you need bigger strings, either switch to a 64-bit host or use the big array module. Okay. So I'm gonna suggest that if this is a single block, it's a block with a single field, right? Then this will have 32 bits for the beginning, and then it will have a single value that will also be 32 bits. But that is just my gut, and this is a terrible way of measuring this. Blocks and values, what are the difference in these things? So let bindings allocate a new block of memory with 2 words out of available space. Okay. 1 word holds the full field, and the other one the far. Okay, this is for this one over here. Right. The OCaml compiler translates an expression into an explicit allocation for the block from OCaml's runtime system. OCaml uses a uniform memory representation in which every OCaml variable is stored as a value. An OCaml value is a single memory word that is either an immediate integer or a pointer to some other memory. The OCaml runtime tracks all values so that it can free them when they are no longer needed. It thus needs to be able to distinguish between integer and pointer values, since it scans pointers to find further values, but doesn't follow integers that don't point to anything meaningful beyond their immediate value. Okay, so wrapping primitive types inside other data structures that record extra metadata is known as boxing. So when you have a particular block, either you have the integer or you have a box that describes the value. Values are boxed in order to make it easier for the garbage collector to do its job, but at the expense of an extra level of indirection to access the data within the box value. OCaml values don't all have to be boxed in runtime. Instead, values use a single tag bit per word to distinguish integer and pointers at runtime. I guess that's the color bit, the one we saw over here, there. The value is an integer if the lowest bit of the word block word is non-zero, and a pointer if the lowest bit of the block word is 0. Several OCaml types map onto this integer representation, including bool, int, the empty list, unit variance, without constructors. Okay. Value is treated as a memory pointer if its lowest bit is 0. A pointer value can still be stored unmodified despite this, since pointers are guaranteed to be word aligned, with the bottom bits always being 0. Okay, so as a block with a single field containing the double precision float. Slightly confused. So essentially we should expect here to have, we have one allocation for each one of this, right? If we count these allocations, then the number should be close-ish. And I also expect this number of words to be similar to the number of words I have here. But then again, one sec. I'm running something different. So we have, even though we're calling, okay, I don't know what graphics or plot is doing internally, right? So that might be very, very different. But this might not actually yield good results. If I have a look at this and each one of them is a float, then, okay, we have one function call here, another one there, and I wonder if those will actually allocate variables, and blocks in the minor heap as they get called, and I assume they will. The memory has to be there, right? I'm a little frustrated. I like to be able to do this more fluently. Do you have any suggestions on how to grossly estimate the amount of allocations of a piece of code like the one that we have here? So we'll see that, I mean, we have access to some of the functions, right? But I would say if we were to write something in the comments here, right? Iterate will essentially have our allocations multiplied by some constant that is 1. Okay. I am not sure. So at the very least, we will be doing this allocation here. That's for sure. Now, when we call this function, then, how do we do this analysis? I don't know how to do this analysis. So say, but I know how we could try it out, right? So we could say essentially 1.0 minus x for some x, and then gz.print stat stdout. I guess if I run that, what happens if I run this without anything? That will be my baseline. So my baseline here is that gc print stat, this is 71 minor words. And if I do x, and I ignore x, so that it doesn't get compiled away. Then that is getting compiled away. Okay, so let's say I ignore x by x. Print float. Okay, so we have 71, and if we just print something, then I reckon that will give me an idea of how many allocations are required for printing. Okay, so this is the same as this, right? And that's about 8 words, sorry, 9 minor words. So when I call this both together, then I get 71 minor words, and 9, that's 80, right? So what happens when I call iterate, right? If I call iterate with, for example, let's say 1, 0, and this should be 1. So it's going to decrement this 1. I can use 0 here. It's going to decrement this 1 on every iteration until it's done. So I guess this could be a base case. Or, yeah, we wouldn't have a single iteration. All right, let's do the base case. Sorry. The base case is 1, as we see here, right? If we call this function with I equals 1, then it will just return init. As I build this, it fails because, right, print float. If I give it 2 floats, right, and an int, there you go. So we know that the printing was 9 words, the print stat was 71 minor words. So running this should be at least 80, and anything that's above 80, I will assume it's the amount of calls that iterate is having. Confused. I am confused. So this seems to have inlined. Okay. If I do 2, then it should not inline it. And we should have more than 80 minor words. And we have 82. Okay, good. So I guess that will be one allocation for this X, right? But I don't know how many allocations these operations will yield. Interesting. So what happens if I go for 100? Then I wonder what will I get there. Build it. Will I get... So my theory is that the amount of iterations will yield an equal amount of allocations, because the only allocation that we have is for the lead binding that we have in there, and everything else can be inlined, or rather doesn't actually require us to do a minor heap allocation, which I'm not sure if it's right. I'm just saying the words that kind of make sense in my head. So we'll run it, that makes sense. So now I should expect to see about 180. But no, I have many, many more. 278. I am confused. So going back to 2, right? We get 82. If I put a 0 here, then we get 80. Sorry. We get a Stack Overflow. Right. Because this is equals to. If I do less than 1, then it should work. 80, right? If I go to 2, we get 82. And we get 84. Before, when this was equals, we got 82. Yes. So from equality checks to inequality checks, there is a difference. I guess that equality just checks a reference, and the inequality takes something else. So essentially this takes less space than uses less memory. Rather seems to use. But when I go to 100, I get many more. What happens if I go to 3? Just to 3, right? Incrementing number 1. That doubled. So if we go to 4, we expect it to be 86. Okay, one more should be 88. So remember the 0 here was a segfault, but if 1 here was essentially 80, it goes straight into this case, so it gets inlined. But 2 was 2, right? And then 3 was 4, and 4 was 6, and 5 was 8. So if 6 is 9, then 7 is going to be 90 allocations. 92. Clearly did something wrong. Okay. 90 and 5 was 88. Okay, so if what is 10? It will, let me do the math faster. 10 is 98. So essentially when I have a 10, I have 9 iterations over this before I reach the base case, right? And if I am running about 18 minor words each time, and each time I allocate one variable, one binding, that means this binding must be worth 2 words. So let x is worth 2 blocks in minor heap. You can just write that down. Cool. Interesting. So this means that this function, right, iterate will use I minus 1 by 2 minor words. So it's memory consumption, or it's space O n. Is this how you write this down? This might be the 3rd time I do a space complexity analysis of a function. Oh, Ann Montero, hello, hi, really nice having you around. I did not see your comment, and yes, print float seems to be allocating 9 minor words, as you may have seen by now. Cool. Sorry. It's fairly cold here in Sweden nowadays. Don't know if I can see it today here. Stockholm -9. Yeah, didn't show anything weird. Okay, good. I don't have to edit that part out before I upload to YouTube. Thank God. Okay, well, this is interesting, right? Now we have a function and we have the space complexity of it. Actually, I need to know. Is this called space complexity? Analysis. I'm gonna go on a limb and say that it does, based on the little snippets that Google shows on the results. All right, so we have that there, and we know more or less what it takes. So now we can try to figure out what the rest of these things take, right? So here we have in this two below are 80, I think it's 80 minor words, right? I'm gonna remove this for a second. Right, again, 80, good. So now we can take a look at how much random self-init costs. Whoa! Well, I mean, compared to the other things, but this is 1202. And I will expect these two things over here, right? If we put them like that, to not actually allocate anything. I mean, allocate. Yeah, there I would expect them to not allocate anything. Yeah, good. Which means if I put an X there, and okay, if we go back a little bit, then I expect this thing wait, I need to know how much this one costs. I don't know. So random float 1.0 and then print float. And print is 9 minor words. Can remove this thing. So whatever we get, we should subtract 1 to 91 from it. So random float is 3 allocations. I can annotate that here. Allocations plus 2 for binding, right? We can also check float of int, how much that is. So float of int, and this would be like, I don't know, 99.9. Oops, 99. And that's just 1, so it's 291. Okay, so float of end appears to be free. At least to not allocate anything. That's what I mean. Okay, so let's go with that assumption. This would be 2 for binding. This would be iterate, which would be 499 by 2 plus 2 for binding. And this will be just 2. Right? And then we ignore y. So I expect this, right? Alright, so this one is 640 by 2 for all the bindings, and this one should not be allocated underscore, but it might be that it's actually running the 40. By 2. So roughly, this code of this work over here, right, should be. Why are you doing that? No, don't do that. Okay, I tried. I should try to put the comment inside there. This should roughly be. We had okay. I'll do a small bracket here. We had 290 and 82, right, for the random initialization and iterating and printing at the end. So it will print one thing, right? So this costs at 0 memory allocations. If we remove this thing over here, then we have 9 less, which means we should have 1271. Do we? God. 73. And that's 273 minus 71, 100. Well, okay. Okay, so all the numbers add up. By removing this line over here and this thing over here, we should have 1273 allocations. So I'll build and run that. 273, perfect. So rerunning this thing, we should have now some more allocations. And I think we will have 640 by 2, right? and then 640 times we will have this over here. So by 2 again. This is an addition. I will just add all this list together, and then we'll have 640 by 40 by 2, which is this binding over here, and we'll have 640 by 40 by 5, 3 plus 2 over here, and then 640 by 40 by 499 by 2 plus 2, like this, right? And then again by 2, and I think ignore will actually not cost anything. I don't know, I might be wrong. We will deduct the difference and perhaps tweak some numbers after we run it. So we are essentially saying that this will be 4. We will be multiplying 640 by 2 by 2 by plus 40 by 2. Sorry, sometimes it's just easier to do it in silence, which I recognize is not good for you that are listening out there, but I guess you get to see it too. Okay, so let's begin by the beginning. 499 by 2. This is 998 plus 2. It will be 1,000 allocations. So that's 1,002, 1,004, 1,009. So 1,009 by 40. That's 4,360 plus 4 by 640. Oops. By 640. That's 2583. I'm just going to copy the number. I'm going to put it down there. And just to corroborate that I didn't do something weird, I'm just going to go to UTop, drop this in there, which I could have done to begin with. Now that I realize that, I feel like an idiot, but you know how it is. Okay, so same number, good. At least I can do math with a calculator. And let's see how well it does. Building it. I expect a margin of error of a few thousand, but I could be way off. Oops, wrong command. Alright, look at that, that's not too bad. Minor works total. The big number we got the same on, right? And then we have a few 100,000 off. But that's not too bad. Could have been way worse. This could have been like 75, right? And then we'd be like, oh shit, what really happened here? So we overestimated the amount of memory that this would use. Sorry for the detour, but I really wanted to understand how much memory we were allocating to before I went on reading on the tutorial to understand what finalization is and what do they mean? What was the weak module really? I haven't read any of that, so I have no idea what's it about yet. Okay, so I guess we could continue tweaking these, but I think that for a first shot at understanding how it works, I think it's all right. I mean, I guess it's a testament to how predictable the allocation model really is. But I'm also not using any more of any of the more complex or advanced features of the language, so I don't know how it behaves there. It's definitely something that I will keep in mind. Hey, you wanna quickly see how much an algorithm should take in terms of space? Maybe give it a shot in OCaml or Reason. Anyway, let's continue. Let's see some comments there. Oh, thanks, dude. Thanks a lot. Really appreciate the support. All right, let's continue with finalization and the weak module. We can write a function called Finalizer, which is called when an object is about to be freed by the garbage collector. The weak module lets us create so-called weak pointers. A weak pointer is best defined by comparing it to a normal pointer. When we have an ordinary OCaml object, we reference that object through a name, such as let, name, and then an expression, or through another object. The garbage collector sees that we have a reference to that object and won't collect it. That's what you might call a normal pointer. If, however, you hold a weak pointer or weak reference to an object, then you hint to the garbage collector that it may collect the object at any time. Not necessarily that it will, but that it can, right? Sometime later, when you come to examine the object, you can either turn your weak pointer into a normal pointer, or else you can be informed that the GC did actually collect the object. Interesting. I wonder what happens if you get the object garbage collected. I guess that your finalizer should actually include logic that will prevent you from trying to access that pointer. I mean, logic that will prevent the rest of the program from trying to access that object after the GC actually freed it. Let's read on. Finalization and weak pointers can be used together to implement an in-memory object database cache. Let's imagine that we have a very large number of large user records on a file in a file on disk. This is far too much data to be loaded into memory all at once, and anyway, other programs might access the data on the disk. So we need to log individual records when we hold copies of them in memory. The public interfaces to our in-memory object database cache is going to be just two functions. And I can sense that we're going to make a new module to try this out. There will be a type called record, which is in itself a record. It has two mutable fields, the name and the address. And get record, if you give me an integer, I will give you a record back. And synchronize records, if you give me a unit, I will give you a unit back. Nothing goes in, nothing goes out. The get record call is the only call that most programs will need to make. If it gets the nth record either out of the cache or from disk and returns it, the program can then read and or update the record name and record address fields. The program then just literally forgets about the record. Behind the scenes, finalization is going to write the record back out to disk at some later. Interesting. Okay. I'll finish that sentence again. Behind the scenes, finalization is going to write the record back out to disk at some later point in time. The sync records function can also be called by user programs. This function synchronizes the disk copy and the in-memory copies of all records. OCaml doesn't currently run finalizers at exit. However, you can easily force it to by adding the following command to your code. This command causes a full major garbage collection cycle on exit. At exit, GC full major. Our code is also going to implement a cache of recently accessed records using the weak module. The advantage of using the weak module rather than hand-rolling your own code is twofold. Firstly, the garbage collector has a global view of memory requirements for the whole program, and so it's in better position to decide when to string the cache. Secondly, our code will be much simpler. I'm not sure I follow the first benefit. Okay, let's see. For our example, we're going to use a very simple format for the file of users' records. The file is just a list of user records. Each user record having a fixed size of 256 bytes. Each user record has just two fields, padded with spaces if necessary. The name field 64 bytes and the address field 192 bytes. Before a record can be loaded into memory, the program must acquire an exclusive lock on the record. Okay, so the file, each user has a fixed size of 256 bytes. Each user record has just two fields, padded with spaces. The name field 64 and the address 192. Before a record can be loaded into memory. After the memory copy is written back out to the file, the program must release the lock. Here is some code to define the on-disk format and some low-level functions to read, write, log, and unlock records. Okay. One second, I hear music playing somewhere, and I don't know if it's the TV on the other room or if some of the neighbors are having a very loud party. I will also take a small break to get some water. Be right back. Okay, I am back. Let's continue with this. So we have the record type that we talked about before. We have the on-disk format, which is some constants. Low-level load save records to file. Just gonna ignore the results of calling seek with a file descriptor. Right, so this is the nth file, then record. Then the position will be the nth record. The number of record multiplied by the size of all the records. And a seek set. I'm not too familiar with the unique file descriptor or the Unix module in general, so this might take some extra tinkering around, but we'll get somewhere. Just bear with me, be patient. Okay, so writing to a record takes the number the record has on file, and takes the file descriptor for the list of all the records. It seeks to that place, and then immediately afterwards it tries to write the, I guess write has an offset. No, I guess write offsets the file descriptor after you write a certain amount of bytes. So, you know what, I could stop guessing and I could just go into the docs of Unix write OCaml. That will be much better. And we have here that is write of file descriptor, the buffer, the offset, and the length, and yeah, writing len bytes to file descriptor, taking them from byte sequence buff, starting at position offsets in buff. Return the number of bytes actually written. Write repeats the writing operation until all bytes have been written or an error occurs. It doesn't mention that it's going to offset the file descriptor. I assume it does, otherwise we would be overriding the name with the address. Right, so if we started writing, let's say at offset 0, right, then we write name size 64 bytes, and then if we start writing again at offset 0, 192 bytes, then there's an overlap in 64 bytes between this and this that we will lose. So I assume that it will do the offset. And reading will have to be similar. You seek into that record to essentially offset to the right place. I guess you seek to the right place, and then after that, the reading will also move the seek position. What do you call this? Seek position, pointer, current read byte, current seek byte. I don't know. And then we have a lock and we have an unlock, and this is going to use Unix logs, log files or file logs. Let's have a look at the docs here. Lockf puts a lock on a region of the file open as FD. Great. So essentially, the region starts at the current read-write position for FD set by use. Okay. And extend size bytes forward if size is positive, size byte backwards is size if size is negative, or to the end of the file if size is 0. A write lock prevents any other process from acquiring a read or write lock on the region. A read lock prevents any other process from acquiring a write lock on the region, but lets other processes acquire read locks on it. Okay. Huh. Interesting. The flock and ftlock commands attempt to put a write lock on the specific region. The rlock and trlock command attempt to put a read lock on the specified region. If one of several locks put by another process prevent the current process from acquiring the lock, flock and frlock block until these locks are removed, while ftlock and ftrlock fail immediately with an exception. What does the T stand for? Terminate? Try lock? I guess try lock makes some sense. Okay. Lock command. Unlock a region, lock a region for writing, and block if array locked. Lock a region for writing or fail if array locked. Okay, so I'm gonna go with this T, meaning try lock and try read lock. This is interesting. I guess that with these locking mechanisms you can do many things. What happens when a process tries to lock a region of a file that is already locked by the same process depends on the OS. On POSIX compliant systems, the second lock operation succeeds and may promote the older lock from read lock to write lock. On Windows, the second lock operation will block or fail. Thank you, Windows. Cool. So then lock record and non-lock record will try to seek into a particular file descriptor and either wait until the lock is set or released. No, either. And wait until the lock is set or released. That is the right inflection. We also need a function to create new empty in-memory record objects. Okay. I guess this is to be able to append them later on. Because it's a really simple program, we're going to fix the numbers of records in advance. Total number of records, 10,000. Ooh. We get data sets. Our cache of records is very simple. The get record function is very short and basically composed of two halves. We grab the record from the cache. If the cache gives us none, then that either means that we haven't loaded this record from the cache yet, or else it has been written out to disk, finalized, and dropped from the cache. If the cache gives us some record, then we just return record. This promotes the weak pointer to record to a normal pointer. Oh, okay, so the weak pointer already encodes the data as an optional. That wasn't obvious. It makes sense now that I'm aware of it, but I was expecting the finalizer to actually, the finalizer to actually have to, the ability to mutate the reference that internally was held by the weak pointer. Which I guess doesn't make a lot of sense because you would then have to create a new allocation when you finalize if whatever the weak pointer was pointing to is freed. So it makes sense to always have an allocation around it as in form of an optional, so that if whatever you're pointing to disappears, then you just have it on. Huh. But I might be mistaken, so let's continue reading. So the finalizer will take the number and the record, and it will say finalizing record, write record, and this file. I don't know. I guess write record will appear somewhere in the future. No, here it is. Good. And then we have get record. Sorry. It unlocks a record after we write to it, and then we have get record. And get record has a few nice things going on in there. What's the first thing it does? Tries to get through weak.get cache. I'm going to open the documentation for weak here first. I think it's nice to have it around. So it's arrays of weak pointers and hash sets of weak pointers. Okay. The type of arrays of weak pointers, weak arrays. A weak pointer is a value that the garbage collector may erase whenever the value is not used anymore through normal pointers by the program. Note that finalization functions are run after the weak pointers are erased. A weak pointer is said to be full if it points to a value, empty if the value was erased by the GC. Notes, integers are not allocated and cannot be stored in weak arrays. Weak arrays cannot be marshaled using output value nor the functions of the marshal module. Interesting. Create. We create n returns a new weak array of length n. All the pointers are initially empty. Erase invalid argument if n is negative or greater than max array length -1. I didn't know that. What is mine? That is big. But of course, that also depends. That's also big. Length, set and get. When we do a get here, we get an option back. We give it a weak pointer array, and we give the number, the nth cell. Okay, so this is already doing the wrapping to optionals for us, so we don't need to do it ourselves. Cool. So going back here, when we're trying to get the nth element from the cache, if we have some record and we printf the record and return it. And if we don't have a record, then we create a new record that's empty. That is this function over here. And then we're gonna call the finalizer for this record because we're about to create a weak. All right. So we set up a finalizer for this particular record, right? We lock the record, the file in disk by saying the nth record, which is the one you're looking for, right? Should be locked right now, and we read from disk so that we don't accidentally read something while someone else is writing, we log first, which ensures that whatever we read is how to say this, preserves its integrity. Is that the right way of saying it? It's not being modified or manipulated by anyone else at that point in time. And then we take the cache and we set the nth element of the cache to be some record. Which I find it curious. Why does it have to be wrapped in a sum there? Okay. I guess we could, alright. We can use it to set something as empty as well. Okay. Alright. And then we return a record, which already has a finalizer associated with it. Cool. The sync records function is even easier. First of all, it empties the cache by replacing all the weak pointers with none. This now means that the garbage collector can collect and finalize all those records. But it doesn't necessarily mean that the GC will collect the record straight away. In fact, it's not likely that it will. So to force the GC to collect the records immediately, we also invoke a major cycle. So here we will take the array of weak pointers. Is that the right way of saying it? Let's go back. Array of weak pointers. And we will set all of the records that we have there to none, which means all of the records that we have in it and have finalizers associated will be marked for collection. And of course, when they get collected, the finalizers associated to them will be run, which will create write logs for each one of them. And immediately after the writing of the record finishes, they will be unlocked. I wonder if this should be locked for writing first. Did write record do that? No, it doesn't. Huh. Could this be a bug here? And then we do a full major GC, garbage collection, GC pass. So that will actually go through the whole thing, try to clear up everything that's marked to be cleared, which means all of the records that are none now will have the finalizer, run, and essentially what I described a second ago. Everything will be written, and then the record will be unlocked. Hopefully this will ensure that this file at the end of the program execution, or at least at the end of the synchronization, has no locks there whatsoever. Okay, so we have some test code. So we could download this, if it does download. And I will put this in recent GC cache. Cool. So now we can do the same magic we did before. We can just try to rewrite this in place and then move it to change the extension. So we go into cache. We have an example of finalization on weak pointers. This is the in-memory format. At this format, we have to create a new record. So if we download the data that they're using, and the data should be available, there was a link somewhere on here, right? Where was it? GC module, no, should be weak. .bin, there you go. This one over here. If I click, it's no longer there. Okay. So I guess I could create a bunch of records to see how it works, but I also guess. So this is expecting to create some records. There seems to be some interactivity to this program. It defines the library for the cache, and then it defines an example that we can use. Fixed strings, battle truncate the string to a particular fixed length. Interesting. I'm just gonna try to compile this. I think I can do executables, cache. Oh, right. It's libraries, bytes. Is it bytes? Now, what am I doing? Oh, this is what happens when you don't read. You just pattern match very quickly on some words. We have a type error here. It's not a dependency error. So this is saying that expression has type string, but expression was expected of type bytes, because Unix.write takes a string. And this what? Line 30, character 24. Record string. So why is this expecting bytes? Line 30. I am not sure. This looks about right. Read also takes a string. I mean, if I look into the signature of this thing, how is it that they... Okay, just needs Unix. Why? I do not know. Cache RE, line 30. This looks about right to me at least. Right just takes a string and I'm giving it a string. This expression has type string, but an expression was I'm confused. Printf. I am drawing blanks here. I would expect Unix Write to actually take a string and then name is a string, so it's fine. So I'm going to check the reference. And okay, Write actually takes bytes. So I guess the name itself is wrong, and whatever we had in the example is not really accurate. So I wonder if there's a bytes from string. And I guess I created bytes. How do I fill the bytes in there? Bytes, split string, too many params, buffer, okay, so I could do string to bytes helper to bytes, and this will take a string, and in there we'll just create a buffer, and this will be essentially the size of string, the length for string, and then we will add to the buffer the string, and then we will get from that buffer the bytes buff. So we should be able to say to bytes, and that works. Then the should be line 38. Perfect. And now 43 is over there, and now over here. Boom. Perfect. That built. I wonder where can I update this documentation, because it's definitely not up to date anymore. So if I build, I could run this thing. Oops, wrong executable. Cache.x. I will say type the record number load 0 and this should blow up. No, it didn't. Hey, Les P underscore. Absolutely. Quick detour. There's actually a YouTube channel. I don't know. I never know what the name is. And in this YouTube channel, I am essentially uploading everything afterwards. This should not be. I think this is the. How do I go to the viewer? I'm so new to all this, man. Just fine. I'll just go to YouTube. If you go to YouTube and try to follow me on this, and you search for reasonable coding, there is a small chance you will actually find me there. And I know I will find myself because I'm logged in. Then it makes sense for them to show me, you know, my profile first. You can go in there and you can go into videos, and you'll see several videos that I've been doing before. These are not very old. 1 month ago is the oldest. We should probably say 2 months because I really recorded this in early mid-December or so. But here's where every video will end up eventually. So perhaps not immediately after the stream, but tomorrow morning I will take the time to download it and awesome, and put it here and then tweet about it and whatnot. So if you can't stay right now, or if you're joining right in the middle, then hopefully tomorrow you get a chance to watch it. I will do no editing on it yet, so it will be as long as the stream was, but you obviously can watch it in 2x or whatever speed you feel like to try to, or even just leave it on the background, right? Listening to it to get an idea what was discussed or explored. But it's a really good question. Thanks for asking. Cool. So back into it. Let's update this record. Update record, yes. Name, I'm gonna go for Leandro, and address, home. Cool. So if I load this one now from memory, it already has my name and it has a new line and then home. I don't know why the new line is there, but it seems small bug. If I say update this record no, then it will ask me to load something else. So if I do 1, it's empty. So I will do less p underscore. No, what did I do? 1, update this record, yes. Less p underscore, address, internet. And let's do someone else. We can do, yes. And Montero will be included in this record file, I guess. Address. I'm gonna go internet too. Cool. So if I sync this thing, right. So when I call sync here, right, this will call the sync records function, which will essentially fill all of the weak map with non-references and force a full major collection. And it's detached from where I am running it, but if you look at this here, whenever I call get and I didn't get something is where I will call the finalizer, and I will call finalize, which takes a function from some a to a unit and a value of that a type and returns a unit. So I will be setting up the finalizer for this particular record, and this record coming from new record is essentially a value of record type. Note that there's no reference to the weak map whatsoever while we create the value of new record or while we set up the finalizer. It only seems to appear when we afterwards. As in, we create this new record, we set up a finalizer, we do some stuff with it, and then we set that record value into the weak map with the set, and this is the weak map. Well, actually it's not a weak map. I keep saying weak map, but it's not a weak map. We set it into this array of weak pointers, at the nth element, at the nth position, and I am curious as to whether the implementation of the weak array pointers, the array of weak pointers, has anything internal that makes the finalizers trigger the moment, or queue up the moment you set them to none by calling fill. Yes, I don't know. I reckon that there's some internals in there so that the weak module works nicely with the GC module. You probably want to have these two tied up together at an implementation level to be able to make the mark of the elements in the array of weak pointers efficient, so that by the time you call GC full major, or by the time a major garbage collection occurs, then all of them are already marked to be cleaned. What's interesting is that I still don't quite understand how the garbage collector works. Like right now, I understand that there is a major pass, right, that will clear everything that is marked to be cleared. I understand that every value, every block in memory will have a bit that will tell the garbage collector whether it has to be cleared or if it's being used, right? And I understand that there is a minor and a major heap where blocks will be moved from one to the other, but I'm still missing a few pieces. So even though we were able to take a look at this example, and hopefully this reads from disk. No, it didn't. I wonder why. Even if we read from this particular... So what I'm trying to say is that this tutorial did give me a better idea of how things work. I have a better idea of how the GC module works and how I can use it to essentially do complexity analysis on a particular function or algorithm. I have an idea of how to modify different flags inside of the GC, which is very interesting. I haven't explored all of the possibilities that it has inside, but now I know that if I do GC dot, right, and then there will be a type here, which is the control type, and this type essentially has all of these properties: minor heap size, space overhead, verbose, etc. Some of them are mutable and some of them are not. But essentially, I can use set and get to configure the garbage collector, which I had no idea about before. I think that's very interesting. And I also understand what finalization is and how it's a way for the program to be notified about garbage collection, and how the weak module seems to be an interface to those finalizers. So essentially, if you have a program that could benefit from a particular garbage collection optimization, garbage collection, how would you say this? It could optimize its behavior depending on how or when the garbage collector is called. Then perhaps looking into the weak module for building and using weak pointers might be a good idea. And there's a nice example here that describes how we can write a cache that essentially will synchronize itself with a file storage, right, by using Unix locks and weak pointers, so that whenever there is a full major collection, everything that in the cache is set to none, which means it was not read from the cache, we'll have an associated finalizer that will essentially write down to disk whatever modifications you do in a variable, in a particular record. I guess if I was to rephrase that, I would say that the cache that we looked at, the implementation of a cache that's described in here, right, is a cache that by the time your program ends will make sure that all of the records that were modified during the execution of the program are also written down to disk. That seems to be a nice way of, or a pretty good example of how weak pointers could be used for the advantage of a program. Now, I'm not an expert on them, so I'm not sure if there are more examples of it or better examples of it. I guess we could do a little Googling around, searching around. There are some other example exercises here that we could try to do right now. I'm going to read them through and then we'll decide. But I also have a different reference on garbage collection, which is from Real World OCaml. Understand the garbage collector, which I would like to also cover, also read through today. And some of this material might actually be duplicated, but I get the idea that it will allow us to, or at least it will allow me to better, in a more rounded way, understand what the hell is going on with the program as it runs, and essentially what trade-offs am I making when I pick OCaml or Reason Native to build something versus, for example, Rust that doesn't have a garbage collector. All right. Okay, so these are just different ways in which we can expand the caching example that we saw before. Implementing the record as an object and allow it to pad and unpad strings. Extend the program so it acquires a read lock on getting the record, but upgrades this to a write lock just before the user updates any field. Support a variable number of records. Tip: OCaml has support for weak hash tables. Variable length records, which I reckon each record will be prefixed by the length of the record itself. Making the underlying file representation and DBM style hash. And I don't know what this is, so I'm gonna DuckDuckGo it. It's a simple database engine written by Ken Thompson and released by AT&T in 1979. Its database manager can also refer to family of database engines with APIs and features derived from the original DBM. Single key fixes buckets and uses hashing techniques to enable fast retrieval of the data by key. So the database grows as keys are added. They're pre-relational databases. They manage associative arrays. Okay, I will leave this open for further reading. I can close this. And yeah. And then building a cache for any relational database of choice. Or one in particular. Okay, I don't actually, I'm not too interested in looking deeper into this. I understand that weak pointers are useful, but I rather understand better how the GC actually happens under the hood. We can go back to this at some point. Okay. Well, OCaml tutorials, thank you very much. Let's go into real world OCaml, second edition in progress, understanding the garbage collector. And before I continue, I will just take a small pause. So I will be right back. And I should have one of these screens that says, "We'll be back soon," or something like that. And I'm back. Alright, so where were we? We were going to start reading the Garbage Collector chapter from Real World OCaml. Okay, so some of the things might be a little more obvious since we already read something different on the same, some different material on the same topic. Let's just scan through it. And understanding the garbage collector, we have a generational garbage collector, the fast minor heap, and allocating on it, long-lived major heap, allocation strategies, marking and scanning that heap, heap compaction, intergenerational pointers, and finally attaching finalizer functions to values. Okay. So we described a runtime format of individual OCaml variables earlier in chapter 20, memory representation of values, which is actually coincidentally the one that is this one? Yep. The one we were taking a look at beforehand. When you execute your program, OCaml manages the lifecycle of these variables by regularly scanning allocated values and freeing them when they are no longer needed. This in turn means that your application don't need to manually implement memory management, and it greatly reduces the likelihood of memory leaks creeping into your code. The OCaml runtime is a C library that provides routines that can be called from running OCaml programs. The runtime manages a heap, which is a collection of memory regions that it obtains from the operating system. The runtime uses this memory to hold heap blocks that fill up with OCaml values in response to allocation requests by the OCaml program. Alright. So the GC library itself, might actually be just a bunch of FFIs into the C library. And it's a runtime that manages this memory for us. Okay. Mark and sweep garbage collection. When there isn't enough memory available to satisfy an allocation request from the pool of allocated heap blocks, the runtime system invokes the garbage collector. An OCaml program can't explicitly free a value when it is done with it. Instead, the GC regularly determines which values are live and which values are dead. That is, no longer in use. Dead values are collected and their memory made available for reuse by the application. The GC doesn't keep constant track of values as they are allocated and used. Instead, it regularly scans them by starting from a set of root values that the application always has access to, such as the stack. The GC maintains a directed graph in which heap blocks are nodes. And there is an edge from heap block B1 to heap block B2 if some field of B1 is a pointer to B2. All blocks reachable from the roots by following edges in the graph must be retained, and unreachable blocks can be reused by the application. The algorithm used by OCaml to perform this heap traversal is commonly known as mark and sweep garbage collection, and we'll explain it further now. Okay, so generational garbage collection. The usual OCaml programming style involves allocating many small variables that are used for a short period of time and then never accessed again. OCaml takes advantage of this fact to improve performance by using a generational GC. A generational garbage collector maintains separate memory regions to hold blocks based on how long the blocks have been live. OCaml's heap is split into two such regions, the minor and the major heap, right? The small fixed-size minor heap, where most blocks are initially allocated, and a larger variable-sized major heap for blocks that have been live longer. A typical functional programming style means that young blocks tend to die young, and old blocks tend to stay around for longer than young ones. This is often referred to as the generational hypothesis. Okay. OCaml uses different memory layouts and garbage collection algorithms for the major and minor heaps to account for this generational difference. We'll explain how they differ in more detail next. The GC module and OCaml run param. OCaml provides several mechanisms to query and alter the behavior of the runtime system. The GC module provides its functionality from within OCaml code and will frequently refer to it in the rest of the chapter. As with several other standard library modules, Core alters the GC interface from the standard OCaml library. We'll assume that you've opened Core in our explanations. Oi. You can also control the behavior of OCaml programs by setting the OCaml run param environment variable before launching your application. This lets you set GC parameters without recompiling. For example, to benchmark the effects of different settings. The format of OCaml run param is documented in the OCaml manual. You can leave that open on the side. And this seems to be fairly old. Alright. That didn't work. The fast minor heap. The minor heap is where most of your short-lived values are held, so that's where all of your tiny little variables end up. It consists of one contiguous chunk of virtual memory containing a sequence of OCaml blocks. If there is space, allocating a new block is a fast, constant time operation that requires just a couple of CPU instructions. To garbage collect the memory heap, the minor heap, OCaml uses copying collection to move all live blocks in the minor heap to the major heap. This takes work proportional to the number of live blocks in the minor heap, which is typically small according to the generational hypothesis, which is what we saw before, that young blocks tend to die young and old blocks tend to stay around for longer than young ones. The minor collection stops the world that means that the whole application will be stopped, halts the application while it runs, which is why it's so important that it completes quickly to let the application resume running with minimal interruption. So the minor collection stops the world. Okay. So that means every time there's a minor heap GC pass, your whole program is just doing nothing, just cleaning stuff. Allocating on the minor heap. The minor heap is a contiguous chunk of virtual memory that is usually a few megabytes in size, so that it can be scanned quickly. So you have the base, the start limit, and then there's the size between the start limit and the end, and going backwards you have pointers to blocks. The runtime stores the boundaries of the minor heap in two pointers that delimit the start and end of the heap region, camel young start and camel young end. But we will drop the camel young prefix for brevity. The base is the memory address returned by the system malloc, and start is aligned against the nearest word boundary from base to make it easier to store OCaml values. In a fresh minor heap, the limit equals the start, and the current pointer will equal the end pointer. The end. Pointer decreases as blocks are allocated until it reaches limit, at which point a minor garbage collection is triggered. Allocating a block in the minor heap just requires pointer to be decremented by the size of the block, including the header, and a check that is not less than limit. If there isn't enough space left for the block without decrementing past limit, a minor garbage collection is triggered. This is a very fast check with no branching on most CPU architectures. Okay, so essentially we begin here, right? Because the end equals the pointer. And then as we allocate new blocks, then the pointer moves to the left, and then we essentially draw the block here. Okay, and as we keep going to the left, eventually we will want to allocate a block that will be bigger than the limit, assuming that the limit starts on the left, right? And that means we can't allocate this. We need to do a minor GC pass. And I reckon here is where, based on some criteria, some of the things that are on the minor GC, right, that have been here for, let's say, 1, 2, 3 passes, will actually be moved into the major GC to make more room for other things that will die young. Okay, I think I'm starting to get how this works. I may be wrong. Okay, so allocating a block in a minor heap just requires pointer to be decremented by the size of the block, including the header, that's what we just read, and a check that is not less than limit. Good. If there's not enough space, a minor garbage collection is triggered. You may wonder why limit is required at all, since it always seems to equal start. It's because the easiest way for runtime to schedule a minor heap collection is by setting limit equals to end. The next allocation will never have enough space after this is done and will always trigger a garbage collection. There are various internal reasons for such early collections, such as handling pending Unix signals, and they don't normally matter for application code. Setting the heap size for the minor heap. I've never used core by Jane Street, so I am not entirely sure whether it makes sense to have a real world OCaml that doesn't rely on core. But also it feels very in line with real world that the book on OCaml that showcases how a big company uses it uses a library that the big company uses. I don't know. I'll continue reading. The default minor heap size in OCaml is normally 2 megabytes on 64-bit platforms, but this is increased to 8 megabytes if you use core. But because of a bigger memory profile. Okay. This setting can be overridden via the swords argument to a common run param. Or we can also change it with get and set like we saw before. You can change this dynamically and it will trigger a minor heap collection. Alright, this is where I believe it's going to explain how things move from minor to major. I get how the minor works. Essentially, we have this space that will be consumed from right to left, right? And when there is a block that we want to, append from right to left, or prepend if you're reading left to right, that doesn't fit in that space, we will trigger a garbage collection and it will clean up everything that we can, and then the block may fit. That's interesting. The runtime system, okay, I'll start over. The major heap is where the bulk of the longer-lived and larger values in your program are stored. It consists of any number of non-contiguous chunks of virtual memory, each containing live blocks interspersed with regions of free memory. The runtime system maintains a free list data structure that indexes all the free memory that it has allocated. Free list data structure. Data structure is a scheme for dynamic memory allocation and operates by connecting unallocated regions of memory together in a linked list using the first word of each unallocated region as pointer to the next. It is most suitable for allocating memory from a memory pool where all objects have the same size. It's getting a little late here. Okay. And this free list indexes all the free memory that it has allocated and uses it to satisfy allocation requests for OCaml blocks. The major heap is typically much larger than the minor heap and can scale to gigabytes in size. It is cleaned via a mark and sweep garbage collection that operates in several phases. The mark phase scans the block graph and marks all live blocks by setting a bit in the tag of a block header. This is the color tag. And we saw that in here when we were looking at there. There you go. The color 2-bit, right, is the one that's used for the mark and sweep. The sweep phase sequentially scans the heap chunks and identifies dead blocks that weren't marked earlier. The compact phase relocates live blocks into a freshly allocated heap to eliminate gaps in the free list. This prevents the fragmentation of heap blocks in long-running programs and normally occurs much less frequently than the mark and sweep phases. A major garbage collection must also stop the whirl to ensure the blocks can be moved around without this being observed by the live application. The mark and sweep phases run incrementally over slices of the heap to avoid pausing the application for long periods of time, and also precede each slice with a fast minor collection. Right. Only the compaction phase touches all the memory in one go, and is a relatively rare operation. The major heap consists of a single linked list of contiguous memory chunks sorted in increasing order of virtual address. I would love some drawings. I think that for very soon I'm gonna be getting something to draw on so that I can essentially draw or sketch down some of these elements that we're trying to visualize in our heads. Each chunk is a single memory region located via malloc and consists of a header and data area which contains OCaml heap chunks. A heap chunk header contains the malloced virtual address of the memory region containing the chunk, the size in bytes of the data area, and allocation size in bytes used during heap compaction to merge small blocks to defragment the heap. Let me actually digest that. Allocation size in bytes used during heap compaction to merge small blocks to defragment the heap. Right. Okay, so this is the actual usage that we have from a particular block. Since, at least from what I read in the free list here, it's expecting to... It says that it's most suitable from allocating from a memory pool where all objects have the same size. I'm not sure if that's how OCaml is using it though. And a link to the next heap chunk in the list. Each chunk's data area starts on a page boundary, and its size is a multiple of the page size, 4 kilobytes. It contains a contiguous sequence of heap blocks that can be as small as 1 or 2 4 kilobyte pages, but are usually allocated in 1 megabyte chunks, or 512 kilobytes on 32-bit architectures. The GC module uses the major heap increment value to control the major heap growth. And I guess this is what we use to define how fast the heap will grow upon requests, allocation requests. Allocating an OCaml value in the major heap first checks the free list of blocks for a suitable region to place it in. So depending on the amount of memory that you have there in the free list, it will take longer to find the place. If there isn't enough room on the free list, then runtime expands the major heap by allocating a fresh heap chunk that will be large enough. That chunk is then added to the free list, and the free list is checked again. Right, I guess that if either there are no blocks on the free list, or if none of the blocks actually match or fit the block that you want to allocate, then we need to ask more memory to the operating system, and then we run the process again, right? If we had no blocks in the free list, then now we have one that should be big enough for what we want to allocate, because we requested to the OS enough memory to allocate this chunk. And if we have more than one, then we go through all of them until we find the one that we just added. And then, it will succeed. Remember that most allocations to the major heap will go via the minor heap and only be promoted if they are still used by the program after a minor collection. So after a minor collection, anything that was on the minor heap, they will move to the major heap. I really feel like going to Figma and doing a small diagram of this. The one exception for this is for values larger than 256 words, that is bigger than 2 kilobytes and 64-bit platforms. This will be allocated directly on the major heap. Since an allocation on the minor heap will likely trigger an immediate collection and copy it to the major heap anyway. Right. Okay, you know what? I'm actually going to give it a shot. I'm just going to go to Figma, and I'm going to add a new drawing to some of the projects that we already have in here. New file, yes. I'm going to call it recent native and OCaml GC. Cool. Let's just do a small frame so we can draw a little. Right. And we want to say that there will be a minor. This is a little bit too small, but I really just want to have enough of a size so that it's readable as a drawing for the garbage collection, right? So essentially in the minor we will have a block that will have some pointers. I will just make this a nicer color, a little bit transparent. Good. And I am not an expert with this. I think a stroke would be the border, yes. And for border, we can just reuse the same color that we have here. We can make it darker. Ta-da! I don't know. It looks nice enough to me. Oh, okay. And in here, we will have some arrows. Hopefully, yeah, I can do arrows very nicely. So there will be an arrow going to this thing. How do I do arrows? Arrow. Cool. Arrow pointing there, which would be the base. There would be an arrow pointing somewhere here, which would be start. Somewhere here, which would be the limit. And somewhere here, that would be the end, right? So we have base here. And these are start. A limit. And it might not be obvious why I would want to replicate some of the drawing right now, but it will be in a second. I have some more power around how to do steps for this thing, right? So when we begin, we have this whole block that is free. This, okay, one more pointer here, if I'm not mistaken, which is should be here. I'm gonna go back to that in a second. The PTR, the actual point. Oops. Here. That's where I was. So I'll just duplicate this. Okay. So whenever we begin, we have this memory here that will have some size. Let's say this size is 256 kilobytes, right, in total. And whenever we do a new allocation that goes straight to the minor, let's say just one integer, then what we'll try to do is we'll try to feed a block that will look just like that, starting, assuming that the pointer started at that position, right, not necessarily at the end. We may have some other things already in there. We want to allocate this one thing here, which could be just one int, right? And then because it fits, we just move the pointer all the way here, and we continue doing the same thing as we allocate more things until eventually, right? Sorry. In this case, start and limit seems to be always the same. We could move the limit from the start, but if I keep it the same, also makes the diagram a little easier to read. I'm just going to put this in the middle. There we go. Cool. And if we continue this way, right, we'll end up with a bunch of other blocks. I'm just going to remove the name now. I'm just going to put the blocks there. Right? Oh, my bad. Like that. And so far we have triggered no minor collection, right? And I think it also makes sense to, oops, just so that this diagram is complete, to put that there. Right? So going again, we begin with this minor heap, right? And we essentially have, no, okay, this doesn't make sense. I'm going to remove that a little bit from there, and I'm just going to move this pointer to say that pointer and end are the equals, and then we have one block that's fairly big that we allocated originally. Sorry for all the changing of stories. No, I want to talk to that one over there. Which one is that? Yes, you. Go there. I have two of you. Okay. That explains it. Okay. So we begin in the first image with an empty heap, and then we do an allocation, and of course the pointer goes back to the left. The start and limit are pointed to the same position in memory. And as we continue allocating more things, the pointer keeps moving to the left. as you can see. Then at one point we will try to allocate something, the next block, right? And the next block will actually I need to make this frame a little bigger. No, that was too big. Okay. This next block, right, we'll try to allocate another thing that doesn't fit. And it's very easy to see that it doesn't fit, right? So I'm going to actually put it in a hue that makes sense, so reddish, right? So that doesn't fit in there. And of course, because it doesn't fit, we're forced to trigger minor GC. And this is the first time we trigger minor GC. So let's say that at this point in time, I'm going to write down here I'm actually going to move this around a little bit. I'm going to put this in the middle and make it bigger. Yes. So somewhere here, we were saying allocations happening. And then right here we say first allocation that won't fit. There might be a better name for this. So by now we can check which one of these values are not being used, and if we find any that is being used, right, then we can move it around. So actually the size of the heap doesn't really matter anymore here. I can also do a little, just wait, I messed something up after removing the sizes. Before removing the sizes, I messed up the arrows. Oh, those are still messed up, okay. Never mind about that. I'm just gonna move this below. Cool. So first allocation that won't fit, and then we do a first GC pass. And then this one is not here, right? And we found that all of these blocks could be removed. So we have essentially so if I understand correctly, what's happening here is that the moment that we find we have an allocation that won't fit in the minor heap, we will try to remove everything, right? And then the things that are still being used are going to be sent into the major heap. So I'm gonna have to okay, fine. I am in a small conundrum in that I'm gonna have to do the same drawing on the side and might need to explain both things at the same time. So assume to fit. Cool. And then we can do the major heap as in green. But I do not know how the major heap is actually So I think this is how things work. Of course, if you know best, oops, if you know better how it works, then let me know. I'm gonna take a screenshot of this. Actually, I'm gonna space it a little bit more. Okay. All right. So I think this is how the minor heap GC works. I will just out of curiosity drop this in general and ask. Actually, I think I could go into OCaml native development. Maybe might be better. Hello. Doing a live stream. The garbage collector for RC020 native. And so far, I'm trying to make sure I get how the minor heap GC works. Is this representative? And I think desktop screenshots. This last one. Cool. Okay. Oops. So while I await on that, I'll continue reading. Memory allocation strategies. The major heap does its best to manage memory allocations as efficiently as possible and relies on heap compaction to ensure that memory stays contiguous and unfragmented. The default allocation policy normally works fine for most applications, but it's worth bearing in mind that there are other options too. The free list of blocks is always checked first when allocating a new block in the major heap. The default free list search is called next fit allocation, with an alternative first fit algorithm also available, which I reckon happens the moment that we have to request something. Request more memory. Okay, so it tries. Oh, thanks you for tuning in, dude, or lady, person from the internet. That should be the default, way of addressing individuals on the internet. Yeah, absolutely. Have a good night. Next fit allocation keeps a pointer to the block in the free list that was most recently used to satisfy a request. When a new request comes in, the allocator searches from the next block to the end of the free list, and then from the beginning of the free list up to that block. Okay, next fit allocation is the default allocation strategy. It's quite a cheap allocation mechanism since the same heap chunk can be reused. I lost myself in the text. Since the same heap chunk can be reused across allocation requests until it runs out. This in turn means that there is good memory locality to use CPU caches better. And first fit allocation. If your program allocates values of many varied sizes, you may sometimes find that your free list becomes fragmented. In this situation, the GC is forced to perform an expensive compaction despite there being free chunks, since none of the chunks alone are big enough to satisfy the request. First fit allocation focuses on reducing memory fragmentation and hence the number of compactions, but at the expense of slower memory allocation. Every allocation scans the free list from the beginning for a suitable free chunk, instead of reusing the most recent heap chunk as the next fit allocator does. Right. For some workloads that need more real-time behavior on the load, the reduction in the frequency of heap compaction will outweigh the extra allocation cost. I actually need a break. I'm starting to read things that are words but don't make any sense when read together. Okay. I will be back in a moment. I will leave you with the minor GC illustrated, which might be wrong, but if it is wrong, let me know. And I am back. Right, I see nobody commented on the native development channel, but it's also quite late. I took a moment to try to think a little bit about how the two algorithms that are being used for allocating memory in the Major Heap could work. All of a sudden, the whole memory model starts to make more sense, and I start to see more clearly the cost of running some of these things. Not too clearly yet, but more clearly than before. Okay, so we can continue reading here, the marking and scanning the heap. The marking process can take a long time to run over the complete Major Heap and has to pause the main application while it's active. It therefore runs incrementally by marking the heap in slices. Each value in the heap has a 2-bit color field in its header that is used to store information about whether the value has been marked so that the GC can resume easily between slices. Blue color on the free list and not currently in use. White during marking is not reached yet, but possibly reachable. White during sweeping is unreachable and can be freed. Gray, reachable, but its fields have not been scanned. Black, reachable, and its fields have been scanned. The color tags in the value headers store most of the state of the marking process, allowing it to be paused and resumed later. The GC and application alternate between marking a slice of the Major Heap and actually getting on with executing the program logic. The OCaml runtime calculates a sensible value for the size of each Major Heap slice based on the rate of allocation and available memory. The marking process starts with a set of root values that are always live, such as the application stack. All values in the heap are initially marked as white values that are possibly reachable, right, but haven't been scanned yet. Okay, that's not set here. It recursively follows all the fields in the roots via depth first search and pushes newly encountered white blocks onto an immediate stack of gray values while it follows their fields. I am so lost right now. When a gray values field have been all followed, it is popped off the stack and colored black. There's talk about heap compaction. I wonder why this doesn't have a tile on the left hand side. I think I'm doing a poor job on the Major Heap side of things. I might need a second, either a second stream or some time to actually read and parse this and be able to come up with an illustration such as the Minor Heap one that will make sense for me when I look at it, and hopefully will make sense to other people as well when they look at it. So I'll skip the compaction and I'll read a little bit about the mutable write barrier, because I've heard about this before. I've heard that the moment you start mutating some things, then there's a lot of optimizations that can't be done anymore, and I would like to understand a little bit more about that. Okay. The write barrier can have profound implications for the structure of your code. It's one of the reasons using immutable data structures and allocating a fresh copy with changes can sometimes be faster than mutating a record in place. The OCaml compiler keeps track of any mutable types and adds a call to the runtime caml modify function before making the change. This checks the location of the target write and the value it's being changed to, and ensures that the remember set is consistent. Although the right barrier is reasonably efficient, it can sometimes be slower than simply allocating a fresh value on the fast minor heap, and then doing some extra minor collections. Let's see this for ourselves with a simple test program. You'll need to install the core benchmarking suite. I am not doing that right now. Okay. So essentially we have two types, one for mutable and one for, and one with immutable values. So one is recursively iterating by mutating on a value of type T1, where both values are being updated on every recursion, and the other one is essentially passing on the new count and the new iterator immutably. And when we run this, and it's been run a million times with two bench cases and the same initial values, we'll see that the immutable is actually taking less time to run. There's a stark space-time trade-off here. Right. The immutable version takes significantly longer to complete than the immutable one, but allocates many fewer minor heaps towards the immutable version. Minor allocation in OCaml is very fast, and so it is often better to use immutable data structures in preference to the more conventional mutable versions. On the other hand, if you rarely mutate a value, it can be faster to take the right barrier hit and not allocate at all. The only way to know for sure is to benchmark your program on the real-world scenarios using core bench and experimenting with the trade-offs. Okay, yeah, that's a very sensible way of approaching it. The command line benchmark binaries have a number of useful options that affect garbage collection behavior. The no compactions and stabilized GC options can help force a situation where your application has fragmented memory. And I think we got a ping somewhere. Okay, not related to the it is Discord, not related to the stream. We can take a look later. This can simulate the behavior of a long-running application without you having to actually wait that long to recreate the behavior in a performance unit test. Right. Okay. Interesting. And lastly, attaching finalizer functions to values, which we saw before. OCaml's automatic memory management guarantees that a value will eventually be freed when it's no longer in use, either via the GC sweeping it or the program terminating. It's sometimes useful to run extra code just before a value is freed by the GC, for example, to check that file descriptor has been closed or that a log message is recorded. Alright, I'm starting to get the idea that the finalizers have nothing to do with weak pointers, and they could have been introduced in the tutorial separately from them. So what values can be finalized? Various values cannot have finalizers attached since they aren't heap allocated. Okay. Some example of values that are not heap allocated are integers, constant constructors, booleans, the empty array, the empty list, and the unit value. The exact list of what is heap allocated or not is implementation dependent, which is why core provides the heap block module to explicitly check before attaching the finalizer. Some constant values can be heap allocated but never deallocated during the lifetime of the program. For example, a list of integer constants. Heap block explicitly checks to see if the value is in the major or minor heap and rejects most constant values. Compiler optimizations may also duplicate some immutable values such as floating point values in arrays, right? This may be finalized while another duplicate copy is being used by the program. Okay. For this reason, attach finalizers only to values that you're explicitly sure are heap allocated and aren't immutable. A common use is to attach them to file descriptors to ensure they are closed. However, the finalizer normally shouldn't be the primary way of closing the file descriptor, since it depends on the GC running in order to collect the value. For a busy system, you can easily run out of a scarce resource such as file descriptors before the GC catches up. Okay, that makes sense. And then it explains how to use a heap block. All right, this is an interesting world to get introduced to. I reckon that this live stream could have been called an introduction, or like starting with the garbage collector in OCaml and Reason. I am very, very happy that I managed to understand both how the minor heap works and how the GC could be illustrated in like a step 0, 1, 2, or 1 to n, and then there's a step n+1 where, boom, you get a minor GC pass, and that's where things get sent to Major Heap or Garbage Collected. And then, of course, the next step will be retrying this, which means this block will actually fit here, right? I'm happy with that. I'm happy that we took a detour to try to analyze the space complexity of our very small iteration function, the one that we have over here, A. To be able to say, oh, this is exactly how many allocations this program will run, and it's honestly not a hard process. It's tedious in that you need to understand at the very least, you need to know some of the basic allocations that some things take. For example, each one of the bindings will take 2 allocations, and then each of some functions like apparently random in self-init takes 1202, and that when your function just returns something that's already allocated, it will do no allocations. And of course, this comes a little bit with the practice of doing it, I presume, right? I'm just learning these things right now. But it was very nice to be able to afterwards, right? Look at the function, annotate how many allocations we were expecting, do the math, and see that we were not that far off. You know what I mean? It's like we're definitely on the same order of magnitude of allocations. So it wasn't terribly off. If anything, we over allocated a little, which means our program runs better than we expected it to, which could be due by some optimizations that the OCaml C compiler is doing for us automatically. So that, plus the fact that we managed to go through not one but 2 different pieces of literature on garbage collection, I am trying to make sense of what the different modules for using it are, and essentially dig into some tangential topics like weak pointers or locks would make it, for me at least, a very successful live stream, even though I am incredibly tired and I really wanted to finish both the minor and major heap to the point where I will be able to essentially jump on a book like the Garbage Collection Handbook, and maybe a week from now be in a place where I can start looking or into helping someone like Sander Spice with his work on the WASM compiler, the WebAssembly backend for OCaml. But from 0 to somewhere, I think this is pretty good. I think it's a start. We can build on top of this. So without further things to comment on, I think I'm going to call it a night. I want to thank everyone that was part of this, everyone that commented. If you like what you saw, you can of course just follow me on Twitch and go to the events page every now and then to check what's going to be scheduled here. In the past, I've heavily used events to schedule if this reloads filter past. I don't think it does reload. This might be a Twitch bug. I've heavily used Twitch to schedule events and try to get people to watch them or to be present during the live stream on a variety of topics. So if you are interested in any of these things, when you go to this page, you'll see something slightly different where you can click on subscribe here or notify me or remind me, and it will send you an email and it will tell you, hey, this thing is live, you should go check it out, and so on. And of course, if you liked it as well, feel free to go to the YouTube channel and subscribe. All of the videos are there right now. They will be, this one in particular will be available here tomorrow by the morning. And yeah, I guess that's it. I will make the code that we worked on today available on github.com RC020. I think I'd like to make that repo right now. Yeah, I'll do that. New RC020 public ignore, and I'm gonna ignore the build and Merlin, and yeah, that should be all. So initial commit. Remote at origin, and this should be cool. There it is. Small trash can. Small exploration of the recent OCaml Garbage Collector. That did work. Okay, I'm just gonna put a good old emoji in there. Save. Cool. Okay, you can take a look at this repo if you want to see the source. It should be buildable. The data is also here as well. Should be, look at that. You can read my name, and if I do raw, there should also be Ann Montero. I don't know why the Lisp, what was it, Lispel? Lesp_ person wasn't there. Sorry about that. The program had a bug apparently, and you didn't make it to the commit. Anyways, thank you for everything. Have a good night, and as always, stay reasonable.